film presentation will explain and demonstrate the principles of short-circuiting metal transfer electric arc welding as discussed in these books and others available from the publisher. The short-circuiting metal transfer method is a system of joining metals. It utilizes several basic components. One is the constant potential type welding power source, which maintains a relatively constant arc voltage throughout the entire current range of the power source. A continuously fed wire electrode is provided from a spool of wire positioned on a wire feeder and control unit. The control unit permits control of wire feed speed. An externally supplied shielding gas does several things. It protects the welding zone from the air contaminants and helps to create a stable weld puddle. The shielding gas and the welding wire electrode are brought to the point of use by a gun and cable assembly. These are three major methods of applying the gas metal arc welding process: short-circuiting transfer, spray transfer, and flux core globular transfer of metal. Short-circuiting is referred to by many different names, such as short arc, MIG welding, dip transfer, and others. Both spray transfer and flux core are basically for heavy metals. Nearly all commonly welded metals may be joined with the gas metal arc welding process. But in solid wire, mild steel welding, a very large percentage is done with the short-circuiting method. This report will cover short-circuiting metal transfer on mild steel applications. This short-circuiting transfer action took place in a fraction of a second. The arc shorts as the electrode touches the work. The shorting action of the arc permits molten metal to solidify between deposits from the electrode wire. This may occur up to 180 or more times per second. If you say 1, 2 to yourself, the impact of something happening 180 times during that 1 second is rather impressive. The alternate off and on action of short-circuiting greatly facilitates out-of-position and thin metal welding. The spool of wire electrode permits continuous welding without the need to stop and start frequently. It is obvious that this method of welding is one of the easiest to use. It is relatively clean. The wire is not electrically energized until the operator depresses the trigger on the top of the gun, and of course is de-energized when the trigger is released. A very safe procedure. The short-circuiting method operates at controlled low voltage and amperage when compared with other methods used within the gas metal arc welding process. While it is generally used on light gauge joints up to 1/4 inch thickness and for out-of-position and overhead welding work, it is also ideal for multi-pass welding of pipe and other similar joints. Minimum removal of surface deposits is necessary between passes. Heat input to the work may be closely controlled. This method offers the ultimate in weld puddle control. Here are the 6 simple, basic steps to follow in getting ready to weld. The operator will rapidly move through them in the setup procedure. The operator has already selected the proper diameter electrode for the job. It is on the wire feeder control and already threaded through the cable to the gun. The power source is on. The wire feed speed is set. It will determine the welding amperage. Then the open circuit voltage is set. The gas is turned on, and the gas flow meter control set. The wire extension on the gun is checked, and the operator proceeds to weld. Looks simple, doesn't it? Well, it is. But let's examine the knowledge that the operator must have before he so easily began to weld. There is a simple step-by-step procedure to use in getting ready to do short-circuiting metal transfer welding. This first step is to select the right wire electrode diameter for the job. This can be done after checking the gauge or thickness of the metal to be welded and determining how much heat or amperage is needed to join the metal. A good rule is to allow 1 ampere for each thousandth of metal thickness as a starting point. Thus, for 16 gauge, which is 60 thousandths under the U.S. standards revised, we could say that 60 amperes would be adequate and then select 35 thousandths diameter electrode for the job. 35 thousandths diameter electrode is known to have an effective amperage welding range of from 60 to 165 amperes. Or going to 12 gauge, or 105 thousandths, we can select 100 to 105 amperes as a good starting point. The chances are that the amperage will have to be increased, but this is a reasonable starting level to melt the electrode effectively. Since the majority of short-circuiting welding is done with 35 thousandths diameter wire, that electrode will be used for all demonstrations. The job is to complete a fillet weld with 12 gauge material. Using 1 ampere for each thousandth of thickness, the chart indicates to start welding at about 105 amperes. While the amperage may have to be adjusted upwards, it is still a good starting point. The electrode selected is 35 thousandths. The ammeter reads 120 amperes as a good welding condition is achieved. While the chart points out that 105 amperes are required to weld 12 gauge material, common sense dictates that we will need more heat to work with a heavier 1/4 inch material. Thus, it is necessary to raise the amperage by increasing wire feed speed to meet the welding condition. As a good welding condition is achieved, the ammeter reads 140 amperes. It is an inherent characteristic of the short-circuiting metal transfer method that the faster you set your wire feed speed, the higher will be the welding amperage drawn from the power source. While each operator will acquire his own skill in selecting the proper wire feed speed for each welding condition, this chart provides a good starting guide. 1 ampere is allowed for each thousandths of material to be joined. 12 gauge material is 105 thousandths. The chart suggests that to obtain the 105 amperage level, the wire feed is 140 inches per minute. 35 thousandths has been selected as the wire size. The wire feed speed is set at 140 inches per minute, which will provide about 100 amperes. Note that the wire feed speed is the only element changed. This idea is very important. Only change one variable at a time when setting up the welding condition. There is minimum spatter. The arc sound is steady and smooth, almost like bacon sizzling. Areas on either side of the weld joint are free of spatter. The weld bead is the proper width. The crown or top of the bead is not overly high, which suggests that good penetration has been achieved. The operator has successfully found the right amperage or wire feed speed to use. Now the wire feed speed is set too high. The welding condition is very erratic. Examination of the weld joint shows a great degree of spatter. The bead is narrow and ropey, with a high crown. This would suggest an excessive amount of filler metal for the joint, and that penetration is likely to be poor. The wire feed speed setting was simply too high for an efficient weld joint to be made in this thickness of material. Deliberately selecting a low wire feed speed of about 100 inches per minute will give the operator a welding amperage of about 75 amperes. The arc action is very irregular. Spatter is present. The bead indicates that the electrode has been melted, but is not properly fused to the base metal. The bead is too small because of the lack of filler wire. An examination of all 3 weld joints shows clearly that too high a wire feed speed will tend to produce spatter and a high crowned bead. Too low a wire feed speed tends to produce a small bead with spatter and inadequate fusion. When the amperage is right for the condition, the bead is of the desired size, properly flat, spatter is held to a minimum, and the arc will sound smooth and steady. The 3 welding conditions may also be illustrated in this manner. With too low an amperage, as shown here in red, there are only about 40 to 50 short circuits per second. At the optimum amperage shown by the blue lines, the number of short circuits per second is about 150 to 170. Finally, as indicated by the yellow lines, we achieve approximately 220 to 230 short circuits per second, where amperage is the highest and arc voltage lowest. The short-circuiting method is a low voltage and low amperage system. Logically, a low voltage setting is selected. Voltages over 21 volts will tend to produce spraying, or a globular metal transfer and not a short-circuiting type of metal transfer. With an open circuit voltage of 24 to 25 volts, the voltmeter indicates 17 volts during welding. This is the actual pressure or voltage under load in the circuit. The arc on and off action is a nice, steady buzzing sound. The weld puddle area shows very little spatter. If the open circuit voltage is increased to 35 volts, there is excessive spatter, and the arc sound is now sharp and rasping. The load voltage during welding goes up to 26 volts. The bead has an irregular ripple, and the edges of the bead suggest poor fusion. Lowering the open circuit voltage to 20 provides a load voltage of 12 or 13. The deposition of filler metal is irregular. The weld joint has a high-crowned bead. Very little penetration is achieved. Rather, the metal deposit is mostly on the surface. When proper conditions are achieved, the bead is properly flat, but not concave or rounded inward, and spatter is minimal. Too high voltage produces excessive spatter and a very irregular bead. Too low a voltage shows spatter plus an irregular excessively high bead, suggesting very poor penetration. It becomes apparent that operator skill must be developed in setting the proper voltage for each welding condition. It is a matter of experimentation, and soon becomes a skill now possessed by thousands of welding operators in industry. Actually, it is seldom necessary to change the slope of the volt-ampere curve for short-circuiting metal transfer in mild steel welding, since the manufacturer will have set the slope to handle most of the conditions encountered. But a competent operator should know how to get the most performance out of his power source. Setting the slope of the volt-ampere curve is extremely simple. The volt-ampere curve is merely a method used by welding power source manufacturers to illustrate on a graph the electrical energy output in volts and amperes of a welding power source. The volt and ampere output values of the power source form points on the graph. When a line is drawn through these points, the output curve is formed. The voltage indicated and its correlation or joining with an amperage value simply states that the power source is capable of providing that amount of voltage at the indicated amount of amperage. Power sources, such as the 250 ampere constant potential or constant voltage machine in use here, offer the opportunity to control the amount of maximum short-circuit current and its rate of response. This graph illustrates that if there were no control over the current, it would simply surge to a very high amperage, far beyond the design parameters of the power source, until the wire electrode literally exploded. Without control over the amount of current, the clearing of the short circuit as the wire touches the work is violent. An intense spatter occurs. The extreme heat is causing the remaining electrode wire to melt or ball up prior to the short circuiting or touching to the base metal. Note the arc reigniting with great rapidity. There is not enough time for a smooth transfer of molten metal. The entire action is literally out of control. By slowing the power source's rate of response and limiting the short-circuiting current, a short-circuiting amperage level is maintained which provides a smooth melting of the tip of the wire, and at the same time achieves a steady response of the current as it reignites the arc following each short circuit. There is a smooth separation of the electrode at the point of contact with the base metal. The violent spatter has been eliminated. Note particularly the steady reignition of the arc immediately following the short-circuiting or contact occurrence. Adding excessive slope, as much as 12 turns of slope, achieves a lower short-circuiting current, the time of electrode contact in the weld puddle increases. Only slope, not voltage or amperage settings, have been changed. Note the stubbing action of the electrode. This is due to a severely limited amount of short-circuit current. There simply is not enough heat to properly melt the electrode or the base metal. Even this greatly reduced amount of current does not return to the point of short circuit quickly, since the response time of the current has also been drastically cut back. With 0 turns of slope or no control at all over the maximum short-circuiting current, there is literally an explosion of current as it surges out of control to clear the short-circuit contact of the electrode to the metal. 8 turns of slope provides the desirable level of short-circuiting current and properly controls its rate of response time as it reignites the arc. With 12 turns of slope, there is inadequate short-circuiting current. The electrode will not be properly cleared as it makes short-circuit contact with the base metal. It is very important to note that all changes in slope were made without changing electrode size or the voltage or amperage settings, which were established for a good welding condition. It is a simple matter to make new slope connections on the 250 ampere constant voltage power source. The first essential step is to be sure the primary current is turned off. Never work with the interior of any power source until you are sure the primary current is turned off. The taps connected to the reactor coils are clearly identified for slope adjustment. A convenient diagram for making tap connections is provided by this manufacturer. While slope in the power source used in our demonstration is mechanically adjustable, a new generation of machines has slope preset within the machine and no adjustment is required. Setting the shielding gas flow is our next step. This is simply achieved by opening the gas valve on the supply cylinder and then the valve on the flow meter. The flow meter is calibrated to indicate cubic feet per hour of gas flow. The most widely used shielding gas for short-circuiting metal transfer welding is welding-grade carbon dioxide. This is particularly true for all mild steel applications. The gas flow for most short-circuiting application is 15 to 18 cubic feet per hour. But in overhead work as shown here, or where drafts exist, the flow rate may be increased to ensure full protection of the molten weld metal. For some applications of mild steel welding, where surface appearance is a critical factor and it is desired to reduce possible spatter to an absolute minimum, a mixture of argon and carbon dioxide is used. Opinions differ on the mixture, but many operators do not exceed 25% carbon dioxide and find that a suitable mix. The short-circuiting metal transfer method is simple to set up and use, but the knowledge behind each elementary step is important. Let's consider the 6th step, which concerns very basic operator performance. The welding current is transferred to the electrode wire by the contact tube. The contact tube should extend slightly past the edge of the gas nozzle. If it is recessed into the gas nozzle, spatter accumulation could develop and seriously disrupt the gas flow pattern. A recessed position would cause longer wire extension. Correct wire extension should be about 3/8 of an inch from the end of the contact tube. If the operator permits too much wire extension, the gas shield is reduced. Large globules build up, probably caused by the additional electrical resistance of the wire length. A sporadic and unstable arc results. These 6 steps, taken in order, provide a very practical guide for the efficient application of the short-circuiting metal transfer method of welding. A new generation of constant potential or constant voltage type power sources have added even greater convenience in applying short-circuiting metal transfer. A major innovation is that slope or restraint of the maximum short-circuiting current and its rate of response is controlled electrically within the power source. Secondly, welding may be done with a remote control system at substantial distances from the power source itself. This is a typical situation that might be encountered where two different welding conditions must be met. On the vertical down corner weld joint, where 12 gauge is joined to 12 gauge, and on the horizontal fillet, where 1/4 inch is joined to 1/4 inch metal, different amperage and voltage values will be required. The operator sets one set of conditions for the 12 to 12 gauge and a different set of conditions for the 1/4 inch to 1/4 inch condition. As the vertical down weld of the 12 gauge metal is completed, the operator simply depresses the trigger all the way down, and the system automatically provides the proper amperage and voltage value needed to weld the thicker metal. This dual schedule convenience is a recent addition to modern electric arc welding and is being installed in more and more educational and industry locations. The short-circuiting metal transfer method of electric arc welding is widely used in both large and small shops. It may be automated for jobs such as pressure vessel work, and multiple welds may easily be set up from separate wire feeders. Semi-automatic applications where both short and long joints are encountered, as well as awkward joint angles involved, are easily made with the process. Welds which must meet code requirements are made with great ease of repeatability. Where the work can be fixtured, the lightweight welding gun permits operators to easily complete uniform and X-ray quality welds on a continuing basis throughout a work shift. Clean, smoothly deposited, and efficient welds of this type are typical. Modern shops encountering all types of welding needs will often bring their shielding gas supply to the welding gun via a piped or manifold system. Wire feeders also may be suspended overhead and out of the way of worker or materials movement requirements. Several operators may work on one job and never get in each other's way. The out-of-position welds made possible by the short-circuiting method permit operators to move rapidly along an entire workpiece, changing smoothly from horizontal or vertical to overhead welds with ease. Large augers of this type may be welded by 2 or more operators working side by side. While skill is obviously required to lay in efficient welds along curving lines, the persistent dependability of the process ensures a very high level of approved weld joints. Where precision pieces must be fabricated, fixtures are readily created, and the entire welding operation again made thoroughly efficient by moving shielding gas supply and wire feeder controls and supplies out of the way of the operator. Operators particularly like this welding method because it is clean, there is very little smoke, and it is so much easier to work with than older methods of metal joining. Management approves of the dependability of the method, and the final users of the finished product appreciate the cost and quality provided.